In mathematics, especially in set theory, a set A is a subset of a set B, or equivalently B is a superset of A, if A is contained inside B. That is, all elements of A are also elements of B. A and B may coincide. The relationship of one set being a subset of another is called inclusion or sometimes containment. The subset relation defines a partial order on sets. The algebra of subsets forms a Boolean algebra in which the subset relation is called inclusion. Definitions: if A and B are sets and every element of A is also an element of B, then A is a subset of B, denoted by, or equivalently B is a superset of A, denoted by. If A is a subset of B, but A is not equal to B, then A is also a proper subset of B. This is written as, or equivalently B is a proper superset of A. This is written as. For any set S, the inclusion relation is a partial order on the set of all subsets of S defined by. We may also partially order by reverse set inclusion by defining, when quantified, a B is represented as X, XA, XB, and symbols. Some authors use the symbols and to indicate subset and superset respectively, that is, with the same meaning and instead of the symbols. And so, for example, for these authors, it is true of every set A that AA. Other authors prefer to use the symbols and to indicate proper subset and superset, respectively, instead of in. This usage makes an analogous to the inequality symbols and less than. For example, if x y then x may or may not equal y, but if x less than y, then x may not equal y, and is less than y. Similarly, using the convention that is proper subset, if A B, then A may or may not equal B, but if A B, then A definitely does not equal B. Examples: the set A equals 1, 2 is a proper subset of B equals 1, 2, 3, thus both expressions AB and AB are true. The set D equals 1, 2, 3 is a subset of E equals 1, 2, 3, thus DE is true, and DE is not true. Any set is a subset of itself, but not a proper subset. The empty set, denoted by, is also a subset of any given set X. It is also always a proper subset of any set except itself. The set X. X is a prime number greater than 10, is a proper subset of X. X is an odd number greater than 10. The set of natural numbers is a proper subset of the set of rational numbers. Likewise, the set of points in a line segment is a proper subset of the set of points in a line. These are two examples in which both the subset and the whole set are infinite, and the subset has the same cardinality as the whole. Such cases can run counter to one's initial intuition. The set of rational numbers is a proper subset of the set of real numbers. In this example, both sets are infinite, but the latter set has a larger cardinality than the former set. Another example in an Euler diagram. A is a proper subset of B. C is a subset but not a proper subset of B. Other properties of inclusion. Inclusion is the canonical partial order in the sense that every partially ordered set is isomorphic to some collection of sets ordered by inclusion. The ordinal numbers are a simple example. If each ordinal n is identified with the set n of all ordinals less than or equal to n, then a B if and only if a B. This can be illustrated by enumerating S equals S1, S2, Sk, and associating with each subset Ts the k-tuple from 0, 1, k of which the ith coordinate is 1 if and only if C is a member of T.